We know our standard derivatives or the integrals of the standard derivatives. When we run into problems with those, we can maybe look for algebraic rearrangements. And barring those, we have the substitution method that we can jump to. Okay, so those are kind of the what we should really be looking at. So again, we want to start with standard integrals. If we can't do that, we go to substitution essentially, right? Or try to do some algebraic rearrangement. But there are ones where none of those methods really are helpful. They don't allow us to integrate. They're still too difficult. And they're usually of this form, f of x times g of x. Those types are ones that substitution and algebraic rearrangements cannot accommodate, and these are not standard integrals. So we need another method, and this method is called integration by parts. So the first part of this lesson, we're just going to look at how we come up with this rule. Now, you don't need to generate this rule yourself, but you should know that it comes from somewhere. And essentially, this integration by parts method is the opposite of the product rule. Okay, so what we do if we can get something with the product rule for differentiation, this process is essentially we should kind of in some ways look at it as the opposite of the product rule. Okay, now it doesn't quite work that quite as easily as that, but this is where it comes from. So if we can let u and b be separate functions, there's our product. So if we differentiate this, I differentiate the u times v function, we get u times derivative of v plus v times derivative of u. So there it is. There's our derivative, our product rule derivatives. So what we're going to do is we're just going to algebraically get rid of that dx. Okay? So we can do that by multiplying both sides of the equation by dx, and that's perfectly fine. The algebra is very consistent. So we can just get rid of the dx, and we end up with this expression. The change in uv is equal to u times the change in v plus v times the change in u. Okay, that's the product rule. So we saw that with the area model, and that made perfect sense. The change in the area u times v, if you recall, there's u, there's v. The change in the area of u times v comes from these three parts, and this is v du, and this area is u dv. Okay, and then we kind of ignore that little bit extra here, du times, it's getting a little bit messy, so I'm just going to clean that up. This little bit there was du times dv, and that becomes insignificantly small, so we just kind of ignore that. So there it is. There's our product rule. Okay, and this is what we get from our product rule. This is the result. Well, if these small changes here equal these small changes here, what we can do is we can sum up these changes and sum up these changes, and we have an equivalent. So we can just say that if we sum up all the u times v changes, or we sum up the changes in area, we get the area. And if we sum this up, we get the sum of all the u times dv parts and the v times du parts. So what we're going to then do is just rearrange this. We just rearrange this so that we move the v times du to the other side of the equation. So we get u times dv, which is here, equals uv minus this part. Okay, so there's a formula, and that's the formula we're going to use. Now, this formula makes perfect sense. It comes from somewhere. Although, when we look at this formula, it's kind of hard to figure out how this formula actually helps us out. And because we really just start with an integral, and we end with an integral. You know, so how is this really helpful? Well, the way this helps us out is that if we have an integral here that we can't integrate, there is an option to rearrange it into this form that's equivalent. And maybe the new integral over here, which is different than the one we had here, maybe this one can be integrated with regular integration methods. And that's the idea behind integration by parts. Okay, it's just basically a formula that comes from rearrangement of product rule, and it allows us another option, another rearrangement of an integral which may be able to be integrated. Okay, so we need to be able to apply this, we need to be able to convert this expression, whatever it is, into a u piece and a dv piece. Okay, so this example here, x cos x dx, we need to be able to separate this into parts, and one part's got to be the u part, the other part has to be the dv part, and to be a dv part, it has to involve the dx piece. Okay, and if we can choose that, we can rearrange it, and maybe, if we're lucky, this integral here will be easier than what we started with. Okay, so we need the right parts. Okay, we have to be able to choose the right parts. There's lots of ways to do it, but we need to be able to select the right parts to get this v du, which is an integral that we can do. And just an extra note here, the dv part here must include the dx term. Okay, so there's a bunch of parts to this. This is why it's called integration by parts.